One of the major applications of Laplace transforms is solving differential equations. As we're going to show in this lecture, you can apply the Laplace transform to a differential equation and change it into an algebraic equation in terms of the s variable. What we can then do is solve that algebraic equation and then take the inverse Laplace transform to find our solution of our differential equation. So it's sort of like a roundabout way of solving the differential equation. The advantage, however, is that we can apply this technique even to differential equations that involve discontinuities. As we've already seen, discontinuities are easy to treat with Laplace transforms. So in this lecture, we'll build up the tools that we need and we'll apply them to a differential equation that we can solve using our standard techniques. And in the next lecture, we'll apply those same techniques to a differential equation with a discontinuity in it. In other words, a differential equation that we wouldn't ordinarily be able to solve, but with Laplace transforms, we can. So the first thing that we're going to need to do is to find out what happens to differentiation with respect to t in S world. That is, what do I get if I take the Laplace transform of a derivative? So these are in your tables. Let me point them out to you, and then I'll prove these results. So we have that the Laplace transform of the derivative of f is s times the Laplace transform, big F of s, minus f at 0, that is the initial condition for f. And we have the corresponding expression for f double prime and f triple prime, that is the second and third derivatives with respect to t. Now you can see that in each of these cases, a derivative with respect to t turns into multiplication by s in the Laplace transform. So 2 derivatives give me 2 multiplications by s, and 3 derivatives give me 3 multiplications by s. But in addition to this, we also get information about the initial conditions of our function. So you can see here I've got the Laplace transform of the first derivative becomes s times big F of s minus f at 0. The Laplace transform of the second derivative becomes s squared f of s minus s times the value of f at 0 minus f prime at 0. So you can see that one of the interesting things here is that we're going to be using the initial conditions, f0, f prime 0, and so on, right at the beginning. So that's in contrast to the case where we were solving differential equations earlier in the course, where we would only use the initial conditions at the very end of the problem. Here we're going to apply the initial conditions at the very start. So let's prove these relationships and then apply them to a differential equation. So here's what we're going to try and prove, that the Laplace transform of the derivative of f is s times f of s minus f0. And we're going to prove this by integration by parts. So we're looking for the Laplace transform of the derivative of f, the time derivative of f. Let's use the integral formula, as always, for this proof. So this is the integral from 0 to infinity of the derivative of f with respect to t, e to the minus st dt. We're going to do integration by parts here, so I'll introduce a variable u is equal to e to the minus st, and dv is equal to df dt dt. So you can see that that's going to give me du is equal to minus s e to the minus st dt, and v is the integral of df dt with respect to t, which is just f. So substituting into this expression here, I'm going to have the boundary terms, so u times v, so that's e to the minus st times v, from 0 to infinity. So here's u, here's v, minus the integral from 0 to infinity of v du. So that's v is again f of t, and du we saw was minus s e to the minus st dt. So that's v du. And we used integration by parts. Now, if we evaluate what's in the square brackets there at t is equal to infinity, you can see that I'm going to get an e to the minus st as t goes to infinity. So that term is going to go to 0. So the first term in that square bracket is 0, because as t goes to infinity, e to the minus t is 0. Next we've got when t is equal to 0, the lower limit. So substituting that in here is going to give me e to the 0, which is 1, times f at t is equal to 0. So that deals with the square bracket terms. Let's take a look at our integral. You can see I've got a minus s here, and that minus s is inside an integral over t, so it's treated like a constant and it can be taken outside. So that's going to become plus s times the integral from 0 to infinity f of t e to the minus st dt. So we recognize that term there, s times this integral here, is exactly s times the Laplace transform of f, and we're left with minus f0. So here we've used f of s is the Laplace transform of f of t. So this proof was just a simple application of the definition of our Laplace transform, so using the integral formula, and integration by parts. And when we did that, we saw that we pick up our original Laplace transform of our original function, multiplied by s, and we subtract away the initial value of f. Now it's easy to apply this result to get the Laplace transform of higher derivatives. I don't need to go through this whole process again of using the integral formula and integrating by parts. I can just manipulate the formula that I have to get the Laplace transform of the second derivative, for example. And the way I'm going to do that is by introducing a new variable, g of t, and that we're going to define as f prime t. So then I can think about what is the Laplace transform of g prime t. Well, applying the result that we just proved in example 1, we know that this is s times, let's call it big G of s minus g at 0, where here big G of s is the Laplace transform of my original function g of t. But I know that g of t is equal to the derivative of f, so I can apply my result again. So this is going to be s times big F of s minus f0. So now I can stick this all into one expression. I've got the Laplace transform g prime of t. Well, remember that g is equal to f prime of t, so the derivative of f prime is f double prime. So I have the Laplace transform of the second derivative, and that's going to be s times g of s, so that's this expression here. So we have s times s f of s minus f0 minus g at 0. And again, g is the derivative of f, so g at 0 is f prime at 0. So now I have my expression entirely in terms of f, f prime, and big F of s, that is the Laplace transform of f. So I can write this as s squared big F of s minus s times f at 0 minus f prime at 0. So both of these results are indeed in your Laplace transform tables, so you'll be able to find them in an exam. And they're going to be very useful for solving differential equations. So let's take a look at a differential equation, example 3. Here we've got a differential equation dy dt plus 4y equals to 8, and we have an initial condition which will be enough to fix any unknown constants in this solution. We're going to first solve this using our standard techniques, and then we'll apply the method of Laplace transforms. So we have a couple of different methods that we can use to solve this differential equation using standard techniques. I'm going to use the method of the integrating factor method. So using standard techniques, we're going to use the integrating factor method. In fact, this is even faster if I use the separation of variables method. You can certainly use the integrating factor method, but we'll save ourselves a little bit of work here. So if you recall, the method of separation of variables just involves taking our differential equation. Let's move that 4y to the right-hand side. And then taking all the terms involving y onto the left-hand side and all the terms involving t onto the right-hand side. And then integrating both sides. So what I'm going to do is I'm going to divide by 8 minus 4y, multiply up by dt, and then integrate both sides. So we can do this integral by substitution. My substitution variable will be u is equal to 8 minus 4y, which implies that du is equal to minus 4 dy. So substituting that in there, I'm going to get minus 1 over 4 integral of du over u is equal to the integral of dt. The integral of du over u is just the log of u. Integral of dt is just t. And I can add a constant of integration. Let's substitute back in what u was and multiply up by that factor of minus 1/4. So that's the logarithm of 8 minus 4y is equal to minus 4t plus minus 4c, which we'll just call b. So here b is equal to minus 4c. After all, a constant is a constant is a constant. Now I can take the exponential of both sides, so I get e to the power of natural logarithm of 8 minus 4y will be equals to 8 minus 4y. That's the left-hand side. And the exponential of the right-hand side will be e to the minus 4t plus b, which we can write as a e to the minus 4t. So there I've used the fact that a is equal to e to the b. So now I can solve this equation by rewriting this term here as a solution for y. So y, let's see, 4y is equal to 8 minus a e to the minus 4t, or y is equal to 2 minus a over 4, or let's call that d, so d here is a over 4. And finally I can fix d by using my initial conditions. So when t is equal to 0, we're told that y is equal to 9. So that implies that 9 is equal to 2 minus d e to the 0, which gives me that d is equal to minus 7. So my solution is y is equal to 2 plus 7 e to the minus 4t. So again, we just use standard techniques to solve this differential equation here. We did that by separation of variables. We brought all the factors of y to the left-hand side. We brought the dt to the right-hand side, integrated, making use of an integration by substitution. We had to, when we did that integration, we picked up a constant of integration that took on a couple of different forms through our calculations. C became B, became A, became D. And finally, we had an expression y is equal to 2 minus d e to the minus 4t. And we used our initial condition, y at 0 is equal to 9, to fix d. So that gives me my solution to my differential equation using our standard techniques. And again, you can use any of the other standard techniques if you like. You can also use the method of integrating factor. You can even use the method we learned for solving homogeneous differential equations if you so like, or non-homogeneous differential equations. And you'll get the same answer, of course. Now let's try and solve this same equation using Laplace transforms. So what we're going to do is we're going to take our differential equation and we're going to take the Laplace transform of each side. So let's write down a differential equation again. I've got y, in fact let me write this as y prime is equal to 8 y prime plus 4y is equal to 8. And we're told that y at 0 is equal to 9. So we're going to apply the Laplace transform to each side. Left-hand side, I've got Laplace transform of y prime plus 4y. So using the fact that the Laplace transform is a linear operation, that means that I can apply the Laplace transform separately to y prime and y. Now we need to use the result that we proved in example 1, that the Laplace transform of a derivative becomes a multiplication by s of f of s minus y at 0 plus 4 times the Laplace transform of y, which we're calling f of s. So again here I'm just using that big F of s is the Laplace transform of y. So you can see here that what I've done is I've turned my left-hand side from a differential equation into an equation involving s's, the initial conditions, and my unknown Laplace transform, big F of s. I'm going to tidy that up slightly. Let's take out the common factor of big F of s. That gives me s plus 4 big F of s. And let's insert our initial condition, y at 0 is equal to 9. Let's take a look at the right-hand side. So we've got the right-hand side is pretty easy. It's the Laplace transform of 4, of 8, excuse me. And so that's going to give me 8 over s. So putting that together, the left and right-hand sides, I get s plus 4, all multiplied by big F of s, minus 9 is equal to 8 over s. So you can see that this is now an equation, an algebraic equation for big F of s. So let's rewrite this now to try and solve for big F of s. I can take that 9 to the right-hand side, divide by s plus 4, and I've got plus 8 over s times s plus 4. So now I've got an explicit expression for big F of s in terms of s. To find my solution then, all I need to do is take the inverse Laplace transform of this to find y. So we're going to need to use our methods for finding inverse Laplace transforms. The first term won't cause us any problems, but we will need to use the method of partial fractions to deal with this term, 8 over s plus 4 times s. So let's write that as a over s plus b over s plus 4. Cross multiply and equate the numerators. So that gives me 8 is equal to a s plus 4 plus b s. That has to be true for all values of s. So I can set s is equal to 0, for example, to get 8 is equal to a times 4, which gives me a is equal to 2. Or I could set s is equal to minus 4 to get 8 is equal to minus 4s, minus 4b, excuse me. And that implies that b is equal to minus 2. So now what we can do is write that f of s is equal to 9 over s plus 4 plus 8 over s times s plus 4. And we saw that that second rational expression there becomes 2 over s minus 2 over s plus 4. Or simply 7 over s plus 4 plus 2 over s. So now we're ready to apply the inverse Laplace transform. So we have that y of t is going to be the inverse Laplace transform of big F of s. So we get 7 times the inverse Laplace transform of 1 over s plus 4, which is e to the minus 4t. And we've got the inverse Laplace transform of 2 over s, and that's just going to be 2. So we actually get exactly the same solution that we got using our standard methods. Now, that wasn't a whole lot less work to calculate the solution to that differential equation using the Laplace transform method. And indeed, it is not usually all that better to do it for general kinds of differential equations that we've seen before and that we have methods to solve. On the other hand, it is going to be useful when we need to solve differential equations involving discontinuities, because when we deal with discontinuities, our standard methods completely fail. And the Laplace transform of a discontinuous function becomes nice and continuous, and we can deal with that, as we've seen. Now we're going to show examples like that in the next lecture. For the time being, let's continue just to check that we can take the Laplace transform of a differential equation and solve that resulting Laplace transform to get the solution to my differential equation. So let's look at another example, example 4. This is a second order ordinary differential equation. It's a homogeneous equation, that is the right hand side is equal to 0, and we have initial conditions for y at y of 0 is equal to 1 and y prime of 0 is equal to 16. Again, we're going to solve this using our standard techniques, and then we're going to do it using Laplace transforms. Because there's no discontinuities involved in this problem, we can use the techniques that we've learned in this course to solve this second order ODE. It's a homogeneous equation, so we're going to look for solutions of the form y is equal to e to the lambda t. That means that every derivative here in this expression is going to turn into a power of lambda. So I get lambda squared minus 6 lambda plus 8 is equal to 0. This has factors of lambda minus 2 and lambda minus 4. And so I get the solutions lambda is equal to 2 or 4. This gives me that my homogeneous solution is equal to a e to the 2t plus b e to the 4t. So now I can find a and b by using my initial conditions, and you notice that the initial conditions are expressed in terms of y and its derivative, so I'm going to need the derivative of y as well. Let's substitute t is equal to 0 in both of these expressions. And we have that y at 0, which we're told is equal to 1, is given by a plus b. And we have that y prime at 0, which we're told is equal to 16, is equal to 2a plus 4b. So I'm just substituting in t is equal to 0 into this expression. Now let's call these equations 1 and 2. And we're going to solve these simultaneous equations here for a and b. So I can, for example, add together or subtract away 2 times 1 from 2. So let's say we've got equation 2 and we subtract away 2 times equation 1. That's going to give me 2a plus 4b is equal to 16, and minus 2a minus 2b is equal to 2. So the a's cancel here, and I'm left with 2b is equal to 14, which gives me b is equal to 7. I can use equation 1 now to find a. A is equal to b minus 1, which is equal to, it's equal to 1 minus b, which is equal to minus 6. So my solution is then given by y is equal to minus 6 e to the 2t plus 7 e to the 4t. That's my solution using our standard methods. And you notice there that I needed to use my initial conditions, y at 0 and y prime at 0, at the end of the problem to solve for a and b. And because my initial conditions were given for y and y prime, I actually had to take a derivative of y and then solve. So there was a certain amount of calculation to be done there. However, when we use our Laplace transform method to solve this differential equation, the Laplace transform method is going to use the initial conditions right at the start, and it uses them in the form of y at 0 and y prime at 0. So this problem is beautifully set up for solution using Laplace transform methods. So let's write down our equation again. We have y double prime minus 6y prime plus 8y is equal to 0. And I'm going to take the Laplace transform of both sides. So on the left-hand side, I'll have the Laplace transform of y double prime minus 6 times the Laplace transform of y prime plus 8 times the Laplace transform of y. Now let's remind ourselves what the Laplace transform of y prime and y double prime are. So we're going to define big F of s is equal to the Laplace transform of y, which gives us that the Laplace transform of y prime is s times big F of s minus f at 0, minus y at 0. And we also have the second derivative. So that gives me s squared f of s minus s y at 0 minus y prime at 0. So let's use this now in our differential equation. We've got Laplace transform of y double prime. We saw that that's s squared f of s minus s times y at 0, which is 1, minus y prime at 0, which is 16. So that's the Laplace transform of y double prime, minus 6 times the Laplace transform of y prime is s f of s, minus y at 0, which is 1, plus 8 times the Laplace transform of y. So here is my Laplace transform of the left-hand side of the equation. We might as well tidy it up before we look at the right-hand side. Let's take out the common factor of big F of s, which leaves me with s squared minus 6s plus 8. And I've got left over minus s minus 16 plus 6, which becomes big F of s in brackets s squared minus 6s plus 8 minus s minus 10. Okay, so notice here that the coefficient multiplying big F of s here, s squared minus 6s plus 8, actually looks a lot like our expression for the differential equation. So if I had replaced every derivative here with the power of s, I would have ended up with the right coefficient. Of course, there's extra terms here that arise because of those initial conditions, so I still need to do this calculation, but a nice little check is that indeed we have s squared minus 6s plus 8, and that matches the form of the left-hand side of my equation here, y double prime minus 6y prime plus 8y. Now, this is the Laplace transform of my right-hand side. What about the Laplace transform of the left-hand side? Let's have a look at the Laplace transform of the right-hand side. So the right-hand side was just 0, and the Laplace transform of 0 is 0. It's an integral over 0. So this whole expression here on the right is equal to 0. So this gives me my algebraic equation that I need to solve for f of s. So let's write this as f of s as a function of s. So I've got s plus 10 all over s squared minus 6s plus 8. Now I know that that denominator factorizes, so this is going to become s minus 2, s minus 4. And I'm going to write this as, let's call it c over s minus 2 plus d over s minus 4. We have to use the method of partial fractions for this. So cross multiplying, I'm going to get c times s minus 4 plus d times s minus 2 all over s minus 2 times s minus 4. So matching the numerators, you see that this numerator here has to be equals to this expression here. So that's going to imply that s plus 10 has to be equal to c times s minus 4 plus d times s minus 2. And I can select values of s. So let's set s is equal to 4, for example. That's going to give me 4 plus 10 is 14, is equal to c times 4 minus 4 will be 0, and d times 4 minus 2 is 2. So that gives me d is equal to 7. If I set s is equal to 2, I get s plus 10 is equal to 12. And that's equal to c times 2 minus 4, so that'll be minus 2 times c. And I get d times 2 minus 2, which is 0. So I get c equals to minus 6. So my function big F of s now was equal to minus 6 over s minus 2 plus 7 over s minus 4. And I'm ready now to take the inverse Laplace transform of that to find y of t. So the inverse Laplace transform of big F of s is going to be minus 6 times the inverse Laplace transform of s minus 2, which is e to the minus 2t. And we've got plus 7 times the inverse Laplace transform of 1 over s minus 4, which is e to the minus 4t. And so we do indeed get exactly the same answer as we had from the standard methods. So we can see that we can use Laplace transforms as an alternative method to solve standard differential equations that we've already seen techniques of solving. Where Laplace transforms really come into their own, however, is when we're dealing with discontinuous functions on the right-hand side. That is, I'm dealing with a differential equation that is representing a system, for example, that's being forced with a function that is discontinuous. We're going to look at that in the next lecture.